Gas law, we're going to take a look at some of the gas laws. There are several gas laws we're going to take a look at today. We're going to take a look at 4 of them. There are 6 that we're going to talk about, but 4 today. So the nice thing about gas laws problems is that you solve them very similarly. So the first thing you're going to do is you're going to write out what you're given. The second step, you're going to figure out what law you want to use. So in these problems, sometimes something remains constant, so you have to figure out what thing remains constant in order to solve the problem. And then you're going to check to make sure your units match. Because our laws are using proportions essentially, we need to make sure our units are canceling out or convert them as necessary. So temperatures have to be in Kelvin. So throughout this entire unit, you have to convert your temperatures from Celsius to Kelvin if they're not in Kelvin already. And then you're going to plug in your values and solve. So Boyle's law is the first law. He was the first person to discover gas laws. He relates pressure and volume. So Boyle's law is P1 V1 equals P2 V2. So as the pressure decreases, volume is going to increase for this, this law. So this is where we have temperature remaining constant and thus indirectly proportional. So we have an example here of a balloon containing 30 liters of helium at 1 atmosphere. It rises to an altitude where the pressure is 0.25 atmospheres. Assuming the temperature remains constant, what is the volume of the balloon at its new pressure? So in real life, if you go up into the upper atmosphere, the temperature is not going to stay the same, but the problem's telling us to assume the temperature remains constant. Quite often in these problems, that's what happens. You're going to have something remaining constant. In this case, it's temperature. So I like to write out the variables that I have. So I have P1, V1, P2, and V2. Notice there's no temperature for us to worry about here. Oops. So it doesn't particularly matter which you assign as P1 and P2. What does matter is that you have them grouped together. So notice we have 30 liters of helium at 1 atmosphere. So I'm going to make those P1 because I think of it as kind of initial. So we have a volume of 30.0 liters and a pressure of 1 atmosphere. So then we have a change that happens. So the balloon's rising up in the atmosphere to a place where the pressure is only 0.25 atmospheres. So we're going to be solving for V2. So this is our question mark, or this is our X. So what we're going to do, we need to rearrange this equation to solve for V2. So I like to remember this equation and then solve it using just rearrangement. So if I want V2, so if I divide both sides by P2, P2 will cancel out and I'll be left with V2. So P1, V1, P2 is equal to V2. So now I'm able to plug in and solve. My units all match, so I don't have to worry about any unit conversions. So I'm going to have 1 atmosphere times 30 liters all over 0.25 atmospheres. So atmospheres will cancel and I'll be left with liters. And what will the new volume of my balloon be? So our calculator tells us that it's 120 liters. That's the new volume of the balloon. However, we do have to keep in mind sig figs. 1 atmosphere here has 1 significant figure, so we have to round our answer to 1 significant figure. So we're going to say that our new balloon is 100 liters with no decimal place. Sig figs is something we are going to continue to use in this unit, just to kind of keep in mind. Okay, so that's Boyle's law. He was the first person to come up with this theory. The next one, Charles' law, was the second person to come up with it. With Boyle's law, I have a kind of fun way to remember it. If you boil a pot of vegetables. Oops. So boil a pot of vegetables. If you look at boil, it's very similar to the name boil. And then pot and vegetables both have P and V, which are the variables that you're using. You don't have to use this way, but it's a fun little way to help remember it. Charles' Law, he's taking a look at temperature and pressure. Pressure's remaining constant. He's looking at volume and temperature. So you have V1 over T1 is equal to V2 over T2. So we have volume and temperature with pressure remaining constant. So this is something where you have pressure remaining constant. A balloon is a great example of this. Because if you take a balloon, if you've ever bought a balloon in the middle of winter on a very cold day, like if you buy it full of helium, you leave the store, you go outside, your balloon shrinks. That's because of Charles' Law. Or the opposite happens. You leave a balloon in a hot car on a hot summer day, it's going to explode. So that's Charles' Law. So this is a direct relationship. As you increase one, the other will increase. So in this problem, we have temperature. So we have a balloon at room temperature, which is 24 degrees Celsius, with a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What's the new volume? So in this case, we have V1, T1, V2, T2. So we have our initial temperature of 24 degrees Celsius and our volume of 4 liters. Our new temperature is 58 degrees Celsius. This is quite warm, by the way. I don't believe your balloon would stay a balloon if it were heated that much, but we'll see what happens. So because we're working with degrees Celsius, we're going to add 273 to both of these because we want to take it from degrees Celsius to Kelvin, and that's how we do it. Remember, when we're adding up, we align our decimal places, and in this case, we're going to round to the ones place in both, because both of my temperatures do not have any significant figures after the ones place. So we're going to end up with 297 Kelvin and 331 for our T2. Notice also it's not degrees Kelvin, it's just Kelvin. So we're going to be solving for V2. When we solve this for this problem, sometimes students have trouble with it. The way that I always do it is I cross multiply. So we start with V1 over T1 is equal to V2 over T2. So I cross multiply to start. So I have V1 T2 is equal to V2 T1. That way we can very easily rearrange it. The problem becomes is if you're solving for T, sometimes students will solve for 1 over T, which could potentially cause an issue for us. So we're going to plug in our values. We're solving for V2. So V2 is going to be equal to V1 T2 over T1. So we're going to plug in our values. So V1, this is also a part that can be tricky because you're dealing with 1s and 2s. You want to make sure you're working with the right one. So V1 was 4. T2 is 331 Kelvin. And divided by T1, which is 297 Kelvin. So our units of Kelvin will cancel, and we'll be left with liters. So we can now plug this into our calculator and solve. So you end up with 4.4579, which we want to round to 3 sig figs, so we're going to have 4.46 liters for our balloon. And half a liter is a significant amount of volume for our balloon to change, so most likely our balloon would pop. The fun little mnemonic to help us with Charles' Law is that Charles is very tall. So very is V, T is tall. So Charles has volume and temperature related with it. So we have the first two laws. Those are really the major laws. This third law, the Gay-Lussac's law, he's looking at pressure and temperature. So it's P1 over T1 is equal to P2 over T2. This was discovered by two separate people, so they merged their names in order to come up with the name for the gas law. So the thing that's remaining constant here is volume. So in the example problem, we have a aerosol can. If you ever looked closely at an aerosol can, it says do not store at a certain temperature. That has to do with the pressure inside the can. The cans are designed to have a certain pressure inside, and there's some temperature variation that occurs, but if it gets to too high of a temperature, the can would be no longer able to contain it. So it's actually very, very dangerous. So quite often when you have an aerosol can, you have to dispose of it separately. You can't just put it in with the trash. So the gas in the aerosol can that has been used has 1 atmosphere, which is what approximately the atmospheric pressure is for us at 25 degrees Celsius. If it's thrown into a fire, what will the pressure be when the temperature reaches 1201 degrees Celsius? So this is a big increase. This is not something I would suggest you ever try. It is very dangerous. Okay, so we have P1, T1, P2, and T2. So our initial pressure is 1 atmosphere. Our initial temperature is 25 degrees Celsius. Our new pressure we don't know, and our new temperature is 1201 degrees Celsius. So we're going to solve for P2 in this problem, and I would do it the same way as we did the last one. So P1 T2 is equal to P2 T1, and then rearrange for P2, because that's what we're solving for. So P1 T2 over T1 is equal to P2. The other thing we need to do, right now we have degrees Celsius, so we need to add 273.15 to both of these. So we're going to end up with 298 Kelvin and 1474 Kelvin. We can now solve. So our pressure was 1 atmosphere times our temperature 2, which is 1474 Kelvin, all over 298 Kelvin. You should end up with 5 atmospheres, which is a significant pressure increase and something that the can would not be able to withstand. So we end up with 5 atmospheres as our pressure. And a way to help you remember Gay-Lussac's law is Gale plays the trumpet. In actuality, you could be tennis or the tambourine or anything that you could play would work for this mnemonic, but as long as you have a T and you can make it unique and your own. But Gale plays the trumpet is a way to help you remember that Gay-Lussac's law is P and T, which is pressure and temperature. The combined gas law combines all the variables together. So you have P1 V1 over T1 is equal to P2 V2 over T2. So the nice thing is all of the previous 3 equations you can get from this equation if you just cover up the variable that's remaining constant. So for example, if you wanted Boyle's law, you could remove temperature from your equation and you have Boyle's law. So it makes it nice because you don't have to remember all of them. You can just remember this one. You will be asked sometimes which gas law are you using to be aware of whose law it is, just to be advised of that. Most often in a combined problem, this is a great example, you're going to end up at standard temperature and pressure. Standard temperature and pressure allows us to be able to do more calculations. You could potentially do a stoichiometry problem with it or some other analysis of it. So that's usually how it ends up occurring. You do have a lot of variables. In this problem, we want to know the volume. So we're going to be solving for V2. I still rearrange this the same way as the others. P1 V1 T2 is equal to P2 V2 T1. So we're going to be solving for V2. So we'll have P1 V1 T2 all over P2 and T1 equal to V2. So write out my variables. So our initial pressure is 153 kilopascals. Volume is 30 liters. And temperature is 313 Kelvin. So in this problem, they gave you Kelvin, so you don't have to convert it. You're solving for V2. Your pressure and temperature are at standard temperature and pressure. So you would need to know what standard pressure and temperature are. So standard temperature is 273.15 Kelvin. Pressure is 1 atmosphere. However, we're in kilopascals. So I would, if it were me, I would just do 101.3 kilopascals, because that way I don't have to do a unit conversion. Otherwise, you're going to have to convert kilopascals to atmospheres. So now we're able to plug in our values and solve, so we can kind of see what happens to the volume. Just kind of looking at the problem, both your pressure and temperature are decreasing. So what happens to volume? It'll be interesting to find out. So we're going to take P1, which is 153 kilopascals, times V1, which is 30.0 liters, times T2, which is 273.15 Kelvin, all over P2, which is 101.3 kPa, and T1, which is 313 Kelvin. So my units of Kelvin and kilopascals are canceling out. I'm left with liters. I now can solve this for V2. So you should end up with 39.5. Note your standard pressure is 101.3. What I'd like you to do, I'd like you to try the remaining practice problems at the bottom here.